So what we're going to touch is, as Anna said, some of the motivations for privacy, and some kind of essentially what concerns users have, a kind of big picture of how privacy works, which I call, from a kind of more holistic perspective, about multiple layers of the blockchain. And if we have time, we won't go deep into NIM, but we'll sort of explain some of the motivation behind what we're doing at NIM and how that could possibly help Cosmos in the future. So let me just get back to here. Let's wait one sec. Okay, so first thing is, let's think about privacy. I mean, I think an important question is, does anyone even care about what privacy is? So there's surprisingly little, at least published, usability studies. I hope all of you great Cosmos projects are actually talking to your users. But what little we have says that actually people are interested in privacy, but they're very concerned, at least over Bitcoin, which is all we have data on. So about a third of the people do believe Bitcoin is anonymous, which is completely crazy. But that's, again, talking to non-technical users. That's why many of them are using it. And another big section, about half, don't think it's anonymous, but believe it can be used anonymously. However, the vast majority of users, 80% of this study, believe it's possible to follow their transactions, and even a quarter, which is actually I was quite surprised at this, pretty large, have tried to use Bitcoin over Tor. So the essential concern is, Bitcoin users and cryptocurrency users in general are using cryptocurrency in part because they believe it's private, and they are very concerned about not being private. And then there's like a whole other set of users. So this was a kind of collection of random Bitcoin users. My background, which I'm going to overview briefly, is that we also looked into why people are using things like Signal. Why do people are concerned about privacy in general? So we did a large number of interviews with various users, including people in Syria who are fighting ISIS and had all these sort of confusions over Signal versus WhatsApp versus text messages, people involved in the Iranian revolution, and which 2009, which didn't work out very well. And generally, everyone was really concerned about privacy, but there's also a lot of concerns that they needed things to be usable, and that slogans like use Signal, use Tor simply doesn't make sense for lots of people in different countries, because it's impossible to download them due to sanctions on the Play Store, or they don't find them particularly usable. And so we did like a very large study of why people, which we call high risk users. These are people that aren't just using privacy to attempt to hide their cryptocurrency transactions, but actually using privacy enhanced tools because they're afraid of some form of government repression, either theoretically, such as done in civil society with EFF, or in practice, such as people on the ground in Russia, Ukraine, various countries in the Middle East, and developers. And, you can read the whole study. It's referenced at the bottom, but effectively, the take-home message is there is a huge disconnect, and a lot of people in the audience are developers, between the properties desired by developers and what users believe those properties that the software delivering actually is, right? So, particularly came out when we had interviewed people who could suffer short-term concrete physical harm, such as being imprisoned or torture due to security and privacy failures, versus people primarily in the United States and Europe who don't necessarily suffer that in the short term. Although obviously with Trump and whatnot, who knows, things sort of look like they were going that direction in the quote unquote West as well. And the general feeling, which we even got, this is actually a quote from someone in Syria. They said, we really didn't have any concerns about security, but then people started disappearing. And then the essential role of the study was that, people have a lot of concerns over server seizures, but this is very important. There was a huge concern particularly among high-risk users. So these are people who are most likely to be hurt or killed due to failures in metadata collection and being able to use things pseudonymously. And they were pretty irritated that most tools that they were trying to use didn't support these use cases. You can see actually there's much more concern from these users about privacy than there is about things like decentralization, like how many different nodes are running. And people were particularly concerned about their device being seized, which something we often assume is safe in the West, and that people were, people did all sorts of crazy things to hide their contact list and to hide and prepare for house searches. And that, again, everyone really liked things like Tor, and people wanted to use Tor and other tools to prevent metadata collection. But even developers were super confused. And this is where I'm going to kind of take the rest of the talk. So we talked to many developers. I think this is a developer of a German secure messaging app, or maybe it's somebody from Rise Up, I forget. But eventually, some of them basically would say stuff like, oh, well, don't worry, we're not logging anything. And if we're not logging anything, then we're not collecting metadata, and therefore it's private. And that's wrong, right? So I think it's important. Can everyone still see the screen sharing properly? Yes, good. Okay. So I think it's important that there's obviously this kind of looming concern about privacy, both from Bitcoin users and from human rights activists, all sorts of people. But the problem is no one really has a good grasp on what privacy is, right? So, and the reason is there's not a clear definition. In fact, what you have is you have diverse traditions of privacy. So primarily, honestly, coming from not computer science historically, but from the legal sphere. So the modern concept of privacy has developed in the United States, comes from this desire to be not photographed by Samuel Warren and Louis Brandeis, and the right to privacy, from this desire to escape the paparazzi, to have some personal individual space which is not public. And in Europe, things took a totally different direction, right? So Europe obviously had the Holocaust, as the book IBM, The Holocaust, wonderful book, details data processing, even in early stages in the 1940s and 30s, was used to help enable the Holocaust. So after World War II, there was a lot of concern over mass data processing, how to prevent, maybe not mass data collection, but at least regulate and prevent abuse. And this led to a more constitutional framework, which is more about discrimination, but has all privacy aspects, or the general data protection regulation. And so we have these very different legal traditions and very different, feelings of privacy. So as we saw earlier in the user study, some people believe being private simply the right to use a pseudonym, not use your real name. Other people believe it's the right to maybe reveal partially or have multiple personalities. And other people want to reveal absolutely nothing. So the way to maybe think about this in a bit more of a healthy fashion, sort of say, well, there's a spectrum of privacy. On one hand, you're being absolutely anonymous. And on another hand, you're totally identified with your real name. And there's a sort of spectrum in between. And so we're going to deep dive a bit on what this spectrum means. So what this is a classic work that I think everyone should read. It was circulated for about 10 years before officially published. And it tries to say, well, what is really being anonymous? And it comes down to this kind of quite technical definition, not mathematical, but at least technical insofar as that it's a little bit precise, by Feitzman, called unlinkability. So unlinkability is within any given system that does data processing, there are a number of items. Let's assume you're an attacker. You're interested in some of these items. They're called items of interest. And if you observe an item and you want to link it to a user or to another item, you can link it to all sorts of stuff. After the way you define unlinkability is that after observing the item, I can't link it to any other items. And that's kind of abstract, but actually does kind of technically hit the hammer on the hit the nail on the head, so to speak. And so then we can think about maybe historically what kinds of unlinkability are useful. So one big problem a lot of the early cypherpunks had was Scientology would go after them. So they would publish something about Xenu or whatever on a cypherpunks or some Usenet archive, and then some church would go after them and say, you should take this down. And so people really wanted to send email anonymously. And so one way to think about what does it mean to send anonymous emails? Actually, there's two kinds of different anonymous emails. And you can think about this in terms of unlinkability. You have sender unlinkability, where any particular message is not linkable to the sender. So this means I can send the email anonymously. So you don't know my name, but you can receive an email from me. Of course, it's maybe hard to send one back, and that's a whole separate technical problem. But you can see that sender unlinkability is one thing. And you can also have this thing called recipient unlinkability, where the actual, I would like to send a message out, but I don't want to know who receives it. So maybe I'm sending out a emergency call for help, and I'm okay. Or let's say, I'm okay if anyone receives it who's a authorized medic, but I don't really want to know which medic received it. That's a bit of a contrived example, but you can imagine this is very different than sender unlinkability. And you may want both. And what you actually end up having is this kind of more complex and nuanced view of privacy, where you have things like unlinkability, but you also have other things, at least I see in the blockchain space, often kind of mixed up with unlinkability, right? So you see unobservability, for example. Unobservability simply means that the state of items of interest are indistinguishable because they're all sort of the same type. So this could be done, for example, if I'm interested not in seeing if observing if you're when you're online or when you're offline, and let's say I send fake traffic, so it hides the real traffic. This makes it a bit unobservable when I'm sending my real traffic. So that's unobservability. Then you have even another property, which I think a lot of people in the blockchain space are interested in, which is very hard to achieve, which is undetectability. Can I even tell if you're using a system at all, right? And so this, for example, would be something that's useful for censorship resistant, not in the kind of blockchain way of saying, well, how many nodes do I have? If a node goes down, is there a trusted third party? Is my system censored? But more saying, hey, I would like for it not even be known that I'm using Tor. I don't even be known that I'm browsing to go through checking my email. I would like that people not even know I'm using the internet at all. And so these things are typically accomplished through like Signal, through domain fronting, which tries to hide the fact you're using Signal by pretending you're on Amazon or Google. Authentication proxy, which tries to disguise, for example, one kind of web browsing is another kind of more innocent web browsing. And this is actually historically, when people say censorship resistance, sometimes they actually mean undetectability and not lack of trusted third parties. So you can see it gets kind of complicated, right? Privacy actually, there's different kinds of unlinkability. And the next obvious question is, how do I measure unlinkability? How can I say that one system or one kind of system is more unlinkable than another? And I think there's kind of two definitions, which people should know. One is the obvious intuitive one, which is the anonymity set. So this is the total number of users a given item of interest or message can be linked to. And there's a kind of obvious upper bound here, right? So unless your system is actually undetectable, it's not larger than the number of people that use the system, right? So if Tor has 2 million daily users, obviously anonymity set of Tor, at best, right, would be around 2 million, though, the circuits are much smaller. So in reality, it's much, much smaller. Same with the cryptocurrency transaction. Let's say I'm using Samurai wallet or whatever, and I'm mixing some transactions, or Tornado Cash, and I think Tornado Cash even measures this on their webpage, right? You can say, well, how many other cryptocurrency transactions am I mixing with? Is it 10 people? Is it 100, right? So is it 1,000? Is it 10,000? That's my anonymity set. But there's another really useful measurement, which is called entropy, right? So entropy is a bit better because the fact of the matter is anonymity sets are not a great measurement because they're sort of timeless. And adversaries observe privacy enhanced systems, blockchains or secure messaging apps or web browsing like Tor over time, right? So they could say, if I'm doing a traffic analysis, let's say I'm the NSA, copying all your traffic down, I'm going to try to correlate stuff. And this changes every time I observe a message, I may learn a little bit more about you. So entropy is a very good way to sort of say, given a new usage of the system by a new user, given a number of users, how is the system essentially, do I learn anything? If everything appears could be equally likely, uniformly random, that I don't learn anything. So it's a high entropy system. A low entropy system is obviously revealing something about users. You can do all these nice per measurement messages. So it's very old work that's referenced there from Denises, and Diaz has a similar paper on information theoretic metrics for anonymity. So this tends to be, and this is where this tends to be a little bit different than how cryptographers think about things, but I think it's a very useful way for real world systems. And because real world systems, and this is kind of my second big point before we delve into the weeds a bit, real world systems, the internet is a great real world system. So you have this thing called the OSI model. And the internet, you can imagine, has layers. There's bits, there's the Ethernet, what goes through the cable, there's the MAC address, there's the IP address, there's applications on top of this, which could be, for example, monitoring you via cookies. And these are on different layers in the system. And, packets are composed of frames, are composed of bits, and packets give you essentially data transfer, which gives you applications. And the important thing to remember is that within any given technical system, there's multiple layers. And a leak in one layer of abstraction can lead to the elimination of privacy on the rest of the layers, right? So these are often what you call side channel attacks, right? So the one that a lot of cryptographers think about is, am I releasing by, maybe processing the key for so long, some time information? Does that time information leak anything about my key? But there's also much more simpler models where it's like, well, is like even using the system, sending this much traffic, for example, through a VPN, does the timing and volume of those packets reveal anything about me? And the answer is usually yes. So privacy is very hard because you have all these different layers. And you have different layers in any blockchain system. So layer 0, your kind of UDP or TCP IP stack, your associated networking choices there for your kind of peer-to-peer broadcast. Then you have your layer 1, Bitcoin and Cosmos, your Atom, your Tendermint chain, what's stored on chain, what could even include smart contracts. Layer 2, which are often just other chains, quote unquote side chains, which are really just kind of layer 1s or ZK rollups or these sort of things. But you also can imagine payment channels, all these auxiliary services, and finally at the top, there's application. So when you're building a privacy enhanced application, you have to kind of think, well, can I build on top of a privacy enhanced layer 2 and a layer 1? So for example, could I use Cosmos and Tendermint as my underlying blockchain? And then even with Tendermint and Cosmos, like what happens on the network level? Can leaks on the network level lead to, even if I'm using all the wonderful privacy tech on layer 1, does that hurt me? So you have this and that's why privacy is so hard, because it's not easily reducible to like a zero knowledge proof or a cryptographic, often very fragile cryptographic primitive. It's really this kind of like holistic multi-level system. It's very hard for most people to think in multiple layered way, including myself. And so then the problem is you have all of these different choices, even in a single layer. So I think everyone already knows this. I'm going to go through it pretty quickly. But, again, when Bitcoin and cryptocurrency started, the obvious thing to do is you say, oh, I want to hide my amount. So we just need addition. So you're just going to use something very similar, like an additive homomorphic encryption scheme like Palier. And this is, Liquid, CoinJoin, Samurai, Wasabi, even Mimblewimble is basically just a slight variation on this to be less interactive. But these all have really large packet sizes, and you don't really get too much flexibility in what you can do, right? You can basically do addition. And, with leveled homomorphic encryption, you can't really do exponentiation stuff. And then the next kind of weird world was the world of Monero and now Mobile Coin. We kind of add some secure enclaves on top. But you essentially boil it down to ring signatures. But again, your anonymity set is kind of limited to the number of people in your ring signature, right? So this is not a great technique either. And so I guess the latest and greatest, which I'm not going to really go into, but which other people will, is zero knowledge proofs, which you give, your anonymity set will then equal all the users, ideally all the users that have ever used the system in that particular version. That would be wonderful. And that's where it's people aiming at a Zcash, some primitive stuff like Tornado Cash, which is more of a mixer, so small anonymity sets compared to Zcash, and also new work on Ethereum like Aztec. And I think on the Cosmos level, it's still kind of open season for figuring out what zero knowledge techniques work best on Cosmos. But the great thing about Cosmos is it's so flexible and you don't have these terrible pairing gas costs. So hopefully we can get zero knowledge proofs working on Cosmos. But I think what's interesting is that I do want to just point out, and this kind of motivates NIM, and I'll try to wrap up here in about 10 minutes, is that no matter, like, I don't really care if you're using a zero knowledge proof system, like a ZK Snark, or some newer ZK Snark with one trusted setup like Plonk, as opposed to per circuit trusted setup. Regardless, doesn't matter, because on some level, if you go back to the layer cake, you're still dependent on layer 0, which is the peer-to-peer networking level. And all of these peer-to-peer solutions in the kind of cryptocurrency space, there's a vast variety of them. They're all not so secure and often broken in their own unique and wonderful way, which I kind of overview here. And therefore, you kind of also want to separate these levels, right? So we have concrete attacks Aaron Tramer has a kind of new one here in 2020, where, even if you're using, let's say, a Groth 16 ZK snark on chain, that's wonderful, but network level data can still be used as a side channel to de-anonymize the on-chain level. And people say, well, is this really realistic? Likely so. We have some examples from 2015 that Chainalysis was doing this on a large scale in the Bitcoin network. So Bitcoin is like 10,000 nodes. Back then in 2015, it was probably a few thousand, but regardless, ranked with a few thousand full nodes and observing peer-to-peer traffic, you can get a large enough grasp that you can more or less get most transactions through, observe a huge percentage of transactions, and that was definitely possible with Bitcoin. And when you look at smaller networks, I forget how many full nodes Zcash has, but I haven't actually get that number from that community, but it's a few hundred, right? So it's really easy to observe. And I would assume, I don't really know how many, quote unquote, Cosmos full nodes are there. Most networks are pretty small. So again, observing these peer-to-peer networks is easy. And so it's great that the validators are producing technology like Sentry nodes and stuff to try to prevent this. But the fact of the matter is, passive adversaries that just observe your network are still very powerful. And so Zcash mentions, the authors of the paper are quite intelligent. They say, well, look, we really need to look at this kind of layer 0 technology. We need to use something like a Tor or even a Mixnet. And that's pretty, and so the problem you kind of have with a lot of these technologies, there's kind of a joke in the early days of the internet, that your server is always kind of insecure. So people really focused on using TLS, and that using TLS was like using an armored car to deliver messages between two homeless people living on benches, because it was just so easy to penetrate servers. And, using ZK snarks on blockchains without some peer-to-peer protection are kind of like armored cars. It's kind of the reverse problem, communicating via paper airplanes, right? So we need to, I kind of want to just emphasize this, that you have to really focus on all the levels. And if you don't build on a good networking stack, you're effectively kind of building on a castle on sand. And I think I already covered that. So one way to do this, I'm not going to really go into NIM per se, but I'm going to kind of give a little bit of background on one way to tackle this stuff, which is a Mixnet, proposed by David Chaum, and it's a really wonderful and easy to read paper. And this sort of stuff is not complicated, right? So a lot of zero knowledge proof cryptography, I think, is much more complicated intuitively. Fiat Shamir secret sharing than what we're doing. There's no, for example, polynomials. What you basically sort of say is, hey, if I were going to hide a message, how would I hide it? And the way you hide a message is you encrypt it, but then you basically collect a bunch of them, you mix them up, and it's a little bit like an on-chain mixer. You randomly permute them and you send them in a different order. And there's many variations on how to do this. This is the classical Chaumian batch Mixnet, which is Elixir, where you basically, the mix nodes, you send messages, goes through mixes, comes out. And this technique is really nice because from a cryptographic perspective, you can do some provability over it. So there's that wonderful paper by Chidos et al. On a universal composability treatment of mixnets. A little bit complicated, but does show you can apply formal methods to mixnets. But the problem with mixnets is that obviously, if you look at that technique, sorry, go up again, this is obviously a problem here, right? Because if I'm sending a bunch of messages to Mixer, and I'm not just sending like a few cryptocurrency transactions, I'm sending, bytes and bytes and bytes of packages, the capacity is going to be limited by the weakest Mixnet, the lowest capacity Mixnet. So that's obviously a problem. And people also didn't like Mixnets because it was unclear if they could scale really well, and doesn't seem obvious how Chaumian net scales. So people kind of moved to a different design called Crowds. This is actually very similar to a more recent design called Dandelion. Essentially, it's the same design. And the intuition is quite great. Again, it's like back to anonymity sets. You can only be anonymous in a crowd. Anonymous routing requires you go through these multiple hops. But the problem is, how do you trust the people that are forwarding your traffic? And if you can't trust them, you get these attacks. They can capture your route. They can gain information. This is called the predecessor attack. And so the main result of Crowds was that this is actually much harder than it appears, and that Crowds was kind of well-known broken. So from Crowds came the Tor design, and Tor basically does something similar, crowd ships you through a bunch of peer-to-peer relays, with a lot of the attacks kind of being a little bit controlled by a directory authority system and other great techniques Tor added. And a lot of most of the decentralized VPNs we've seen, Orchid, Sentinel, they're just kind of weird versions of Tor. But the fact of the matter is, even Tor is vulnerable to some kind of traffic analysis, because obviously it's first in, first out on your packets. So they're not mixing them like Chom would mix them. And therefore, you can de-anonymize those packets via their timing and volume information. And at least in closed world experiments by Quan et al., like deep learning gives you, 95% identifiability, which is pretty bad. And I think, regardless, I'm not going to go to NIM. Dave's going to do that later. But NIM tries to develop a way to scale Chaumian mixnets and add fake cover traffic to get some of those nice unobservability properties. And but what I do want to end on is, okay, so we just said, well, look, there's all these different anonymous layer 0 solutions. There's all these different awesome anonymous privacy enhanced layer 1 solutions. Do users care? Can users using this tech? And the challenge I want to leave everyone with is the answer, I believe, is currently no, right? So you have all these different kinds of observers, people that can just read the blockchain, people that can read all the traffic. So, you can define these different threat models. And what we did is we did a sort of large scale study of about 60 users, because again, talking to users is the way you understand what they're trying to do. And I really emphasize this, want the Cosmos community to do more of this. And we just said, well, can anyone buy anything anonymously with Zcash? And if you can buy something anonymously with Zcash, can you do it using kind of Tor or VPN or some form of layer 0 protection? So we did the study. It's like most cryptocurrency studies, a little bit bizarrely diverse, definitely skewed towards white dudes, but more people from Asia and Africa than you would expect. And mostly kind of beginners, but people who think they're... Interesting you discover about cryptocurrency user studies is everyone thinks they're an expert, which is kind of the reverse of what you have in normal usability studies. And we got people to install the Zcash wallet, which actually, most people did decently good at. People did have, while most people could install the wallet because it's just kind of a button or two, people did have trouble distinguishing the Z address from a T address. This is a shielded or private address from a non-private or public address. So this led to some issues. Hilariously, privacy advocates that hate Google often had issues installing the software, and some users would give up due to slow synchronization issues. But the main thing we discovered is that, honestly, when you use privacy tech, there is often this kind of contradiction in development where you say, well, should it be optional? So if you're something users can turn on, and should be on by default. So for example, Signal wants all messages to be encrypted and secure by default. And Zcash is more of like an optional thing, at least in these older wallets like ZKV. I think that's moving more towards being on by default. But the fact of the matter is, having anything where a user has to kind of understand if something is on or not leads to lots of usability issues. And then, of course, we try to get the users to install Tor. That was super exciting for them. And users in general were a bit more successful installing Tor than wallets, but they had some trouble with the binaries and trouble understanding what IP addresses were. And then only they had to buy something, and only about 1/4 people had trouble determining if the privacy was optional, if it's on or off, how the two things work together. And so basically the result is only 1/4 of users could actually get real network level and wallet level privacy on top of Zcash. So I do think we can do better. That's the challenge for the audience here. And I have a minute or two maybe to answer questions. So I hope, so this is very different than your like classical blockchain kind of ZK talk, but I do think some sort of broad overview would be useful. Thanks a lot.